In 2011, nature delivered a devastating blow that changed Japan forever. Over 20,000 lives lost, hundreds of thousands of homes swept away. A 50-foot tsunami crashed into the eastern coastline with such force it left the world in absolute shock. That catastrophic price forced Japan into a decision that would reshape their entire coastline. They would construct an enormous tsunami defense wall stretching nearly 400 kilometers along their most vulnerable shores. Towering almost 15 meters high, designed to absorb millions of tons of water, requiring tens of thousands of engineers and construction precision measured in millimeters. But one critical question haunts this massive barrier. Can concrete actually stop the ocean's fury? Welcome to Macro Forge, where we explore the mega projects that challenge nature's deadliest forces. If engineering that defies disaster fascinates you, hit subscribe. Let's discover how Japan built a concrete Great Wall against tsunamis. For generations, Japan's northeastern coast existed under a threat the entire world fears: the deadly combination of earthquakes and tsunamis. Japan sits directly on the junction of four massive tectonic plates, a geological collision zone where Earth's crust constantly grinds, slips, and produces over 500 earthquakes annually. Most pass unnoticed, some cause minor damage, but occasionally the plates shift violently beneath the ocean floor. When that happens, the entire seabed can rise or sink within seconds. That sudden deformation pushes enormous water volumes upward, creating tsunami waves dozens of meters high that accelerate toward shore, carrying the force of millions of tons. Small coastal towns learn to live with this reality. Red alert warnings over loudspeakers, residents instinctively running uphill the instant ground started shaking. But nothing prepared them for March 11th, 2011. A magnitude 9.0 earthquake ruptured over 300 miles of tectonic plate boundary beneath the Pacific Ocean. The resulting tsunami reached nearly 15 meters high, far exceeding any defense Japan had engineered. That wall of water swept away over 20,000 lives. It flattened more than 120,000 homes. It triggered a catastrophic crisis at Fukushima nuclear facility. The old seawalls, designed for waves reaching only 8 meters, were completely overwhelmed. Entire communities vanished within minutes. Survivors watched helplessly as the ocean erased everything they'd built over generations. Japan understood immediately. The earthquake was merely the trigger. The tsunami was the true killer, and it would happen again. The question wasn't if, but when. They needed something unprecedented, something that could buy precious evacuation time when the next wave came. So they committed nearly 400 kilometers of coastline to a massive concrete barrier, walls reaching 15 meters tall with foundations plunging over 20 meters deep, an investment exceeding $12 billion. Not just construction costs, but upgraded warning systems and evacuation infrastructure. It was a declaration. Tsunamis may return, but 2011 would never repeat. But building it would prove far more brutal than anyone anticipated. Before pouring a single cubic meter of concrete, engineers faced a challenge that seemed almost impossible. How do you design a wall that can withstand nature's most powerful force? They began with data. Every measurement, every video, every survivor account from the 2011 disaster was analyzed obsessively. Then they recreated those conditions in laboratory environments. Artificial wave tanks where scaled models faced simulated tsunami impacts. Engineers adjusted wall height, thickness, slope angles, foundation depth. Each iteration tested to destruction. They needed to understand exactly when and how the structure would fail so they could engineer past those failure points. After countless iterations, they discovered something critical. Height alone wasn't enough. The foundation determined everything. Waves that high carry tremendous hydraulic force. Without proper anchoring, the entire structure would simply topple forward under impact pressure. The final design emerged. Walls between 14 and 15 meters tall, but the foundations had to extend 20 to 25 meters deep, creating massive underground anchors. Wide trapezoidal bases distributing load across maximum surface area. Reinforced steel cores running through the entire structure providing tensile strength concrete alone couldn't achieve. Only when physical models survived extreme testing did they commit to construction. But that was just the beginning of the nightmare. The wall's location wasn't arbitrary. nearly 400 kilometers along the Tohoku coastline in northeastern Japan, the exact region that absorbed the full tsunami impact in 2011. It would extend continuously through Aomori, Iwate, Miyagi, and Fukushima prefectures, forming the longest unified coastal defense barrier in Japanese history. But this coastline presented brutal challenges. Much of it sits on weak, sandy soil that shifts under pressure. Construction would require removing damaged infrastructure that still stood as grim reminders of the disaster. Old homes, twisted power lines, shattered pipelines, all had to be cleared before work could begin. Simultaneously, they had to establish massive support infrastructure, access roads capable of handling continuous heavy equipment traffic, material storage yards, crane platforms stable enough for machines lifting hundreds of tons, concrete mixing stations positioned at intervals along the entire route, temporary drainage systems ensuring construction could continue through Japan's intense rainy seasons. Then came the real engineering challenge. That weak, sandy substrate couldn't support wall structures tens of meters tall. The solution required extensive ground reinforcement. Drilling teams installed deep concrete or steel piles driven into bedrock. They added layers of crushed stone and compacted sand. They stabilized surface conditions through injection grouting. The goal wasn't just preventing immediate collapse, it was creating foundations that would remain stable for decades through countless earthquakes and storm surge events without settling, sliding, or developing structural cracks that would compromise integrity. With foundations stabilized, excavation could begin. But what came next would test every worker's endurance. Excavators began carving massive foundation pits, some sections extending over 20 meters deep. Near the shoreline where groundwater and ocean water met, this created flooding nightmares. Construction crews built temporary retaining walls and cofferdams, keeping seawater at bay while they worked. Pumps operated continuously, removing water that seeped through despite barriers. Once pits reached design depth, concrete base layers were poured, massive amounts. Then came dense steel reinforcement cages, pre-assembled rebar structures so heavy they required specialized cranes for positioning. Foundation blocks followed, extremely heavy, and wide concrete masses designed preventing the wall from being pushed over by powerful wave impacts. Above foundations, workers assembled towering steel reinforcement cages based on the optimized laboratory designs. Formwork was positioned with precision. Then concrete pumping began, section by section. Each block, typically spanning several dozen meters, required perfect concrete mixing and pouring. Too much water weakens the structure. Too little makes it brittle. Temperature control during curing became critical to prevent thermal cracking. Each completed section was inspected rigorously before connecting to the next, creating one continuous barrier stretching along the coast. There could be no weak points, no sections that might fail under extreme loading. The entire structure had to function as a unified system, but concrete walls alone wouldn't be enough. The ocean demanded additional protection. On the ocean-facing side, construction crews installed specialized concrete units designed dissipating wave energy before it struck the primary wall. Tetrapods, those distinctive four-legged concrete structures, Dolos units with their twisted shapes, other energy-dissipating blocks weighing multiple tons each. These weren't decorative. They served critical functions. Stacked in multiple layers around the wall base, they broke incoming wave force, creating turbulence that dissipated energy before water reached the primary structure. Some sections incorporated stepped faces and sloped surfaces, further reducing water surge heights. On the landward side, engineers added soil and crushed rock along with carefully designed drainage channels. Heavy rainfall couldn't be allowed to pool behind the wall, creating hydraulic pressure that might undermine structural integrity over time. Many stretches included walkways or inspection roads atop the barrier. In some locations, the seawall even doubled as local roadway, integrating flood protection with transportation infrastructure, railings, safety fences, access ladders, signage, all added, allowing safe public access while maintaining security. This wasn't just a barrier. It became part of the coastal landscape communities would interact with daily. Then came the complexity that almost nobody anticipated. The wall couldn't simply block everything. Japan's economy depends on port operations, fishing fleets, commercial shipping, tourism. Engineers had to design entry points allowing vessels passage while still providing tsunami protection. This created engineering challenges that pushed technology to its limits. In busy ports like Kamaishi, they constructed top-down tsunami gates. Massive steel panels suspended between concrete towers, operated by hydraulic motors and pulley systems. When tsunami warnings activate, these panels drop vertically from above, sealing harbor entrances like enormous guillotines blocking incoming waves. Other locations employed bottom-up rising gates, normally lying flat on the seafloor, allowing unrestricted vessel passage. Hydraulic systems lift these gates vertically when tsunami approaches, locking into sidewalls, forming solid barriers. This design works in locations without overhead clearance for suspended systems and allows continuous marine traffic without obstruction. But there's a terrifying vulnerability. These gates must deploy within minutes. Hydraulic failures, power outages, debris jamming mechanisms. Any malfunction during critical moments could render protection useless. The entire system represents hundreds of potential failure points across 400 kilometers of coastline. Everything must function perfectly, simultaneously, when lives depend on it. And after 5 to 7 years of continuous construction, mobilizing over 30,000 workers and thousands of heavy machines, it was finally time to discover if this would actually work. The completed tsunami seawall along Tohoku coastline became the largest continuous coastal defense system ever constructed in Japan. Project costs exceeded $12 billion. Construction required coordination between hundreds of contractors, thousands of engineers, and geotechnical specialists working simultaneously on different sections, each requiring custom solutions based on local terrain, soil conditions, and coastal depth. Computer simulations suggested the barrier could reduce tsunami impact forces by 30 to 50%, provide several critical minutes of extra evacuation time, enough potentially to save tens of thousands of lives during a major event. Coastal roads, fishing ports, and residential areas once completely wiped out now had substantial protection against future disasters. But simulations aren't reality. The true test would come when the next major tsunami struck, and critics immediately began questioning whether this massive investment actually solved the problem. Not everyone celebrated this engineering achievement. Many voiced concerns that grew louder as construction progressed. Local fishing communities complained the walls blocked ocean views that had defined their culture for generations. Some argued the barriers gave false security, encouraging development in zones that should remain evacuated. Environmental scientists raised different alarms. The walls altered coastal ecosystems, changed sediment deposition patterns, affected marine species migration routes, disrupted tidal flows in ways that might create unforeseen consequences decades later. But the most serious criticism cut deeper. The wall was designed against a repeat of 2011. But what if the next tsunami is larger? What if it exceeds 15 meters? Computer models show that once water overtops the barrier, the backside becomes a lethal trap. Water pouring over creates waterfalls of incredible force. Communities sheltering behind the wall could face even worse conditions than if no barrier existed. Japan's response remained pragmatic. The wall isn't designed stopping every conceivable tsunami. It's designed buying time for evacuation, reducing impact for moderate events, providing psychological security for traumatized coastal populations. Whether that justifies $12 billion and permanent coastal transformation remains intensely debated. Japan didn't stop with concrete barriers. They revolutionized their entire disaster response infrastructure, early warning systems upgraded with redundant communication channels, evacuation routes clearly marked with signs surviving power failures, elevated refugees constructed in areas where natural high ground doesn't exist. Regular evacuation drills became mandatory. School curricula incorporated tsunami preparedness. Coastal communities developed detailed response protocols. The wall represents just one layer in comprehensive disaster resilience strategy, and the engineering lessons learned spread beyond Japan. Nations facing similar threats studied Tohoku's approach: Taiwan, Indonesia, Chile. Coastal regions worldwide reassessed their vulnerability and defensive capabilities. Japan's response to catastrophe became a case study in engineering, policy, and societal adaptation to existential threats. You've witnessed how Japan engineered a 400-kilometer concrete barrier against one of nature's most devastating forces, investing $12 billion and mobilizing tens of thousands of workers to construct walls that might buy precious evacuation minutes when the next tsunami strikes. The Tohoku coastline that was erased in 2011 now stands behind massive defenses, but questions linger whether concrete can truly stop the ocean's fury. What impressed you most? The engineering scale, the foundation challenges, the hydraulic gate systems? Share your thoughts below. Thanks for watching MacroForge, where we explore the mega projects reshaping our world. See you in the next one.